Greetings. This is to be a lecture on, well, the article is entitled Recent Problems of Induction. And that's something of an unfortunate title, given the fact that it was written, I think, in 1966. So it's not exactly that recent, but that's the title of the article, so that's the title of this particular lecture. And the problems that are raised in that article are still with us. And so we might just say a continuing problem of induction, if you want to call it that. But I'll begin by sharing my screen. Which one? This one, I think. All right, and here we are. So this was an article written by Carl Hempel, Recent Problems of Induction. Why isn't this working? There we go. This lecture is based on an article entitled Recent Problems of Induction by Carl Hempel. But one of the inherent problems with titling an article Recent Problems or modern developments or any of that is that it quickly becomes dated. My point here is only that it was originally published in 1966. Nevertheless, as I mentioned a moment ago, the problems are still with us. So the classical problem of induction is usually what people refer to when they refer to David Hume's problem of induction. Now, often it's been referred to as the problem of induction. As Hume presents it, it's a problem of justification, suggesting that we can't get any justification for induction, and therefore we can't have justification for beliefs which are based on induction. And it results in skepticism, meaning we can't have knowledge. If you recall, what Hume was saying is that knowledge requires a true justified belief. So if we can't have justification for induction, then we can't have justification for anything based on induction, and that means we can't have knowledge for anything based on induction. So it's actually an argument for skepticism. Now, it's not global skepticism. Hume wasn't arguing that we couldn't have knowledge at all. He simply was claiming we couldn't have knowledge of anything that depended on inductive inference. Carl Hempel, more recently, discussed some of the more recent problems of induction. New problems of induction have been presented that are, quoting Hempel, no less perplexing and important than the classical one. However, he argues that they're logically prior to the classical problem. The classical problem cannot even be clearly stated, let alone solved, without some prior clarification of these new puzzles. So he thinks that there are more fundamental problems of induction that need to be addressed before we could hope to answer the problem of induction as presented by Hume. Hempel points out that there are even more fundamental questions to be answered before we can resolve the problem of induction, such as determining what precisely inductive reasoning is. So this he thinks is more fundamental than whether induction is justified. The first question I ask is, what is induction? When is one engaged in inductive reasoning? What is the nature of inductive inference? Again, more specifically, what are the rules or processes of inductive reasoning? What rules should we follow when reasoning inductively? And how is inductive inference or induction in science or elsewhere actually carried out? Induction is a form of non-demonstrative inference, according to Hempel. Non-demonstrative inference, he means effecting a transition from some body of empirical information to a hypothesis which is not logically implied in it. Now, this is a fancy way of saying it's not deductive reasoning, right? So I move from a body of propositions, but the truth of the conclusion is not entailed by the conjunction of those propositions. So the truth of the conclusion actually somehow expands or goes beyond what the evidence presents in and of itself. So that's what makes it non-demonstrative. Hempel refers to sentences specifying the evidence as the premises and to the hypothesis based on the evidence as the conclusion of an inductive inference. Now, the simplest type of inductive inference would be a generalization. Some have characterized inductive generalizations as going from particular instances to a universal claim. So we say, oh, that man's mortal, that man's mortal, that man's mortal. So all men are mortal, probably. Well, that's one kind of inductive inference where I go from specific examples to a generalization. But others have suggested that inductive generalizations always involve from going from information gained from the past to the present experience, right? So claims about the present, which are based on past performance, or perhaps even predictions of the future. Hempel points out that both of these characterizations are imprecise. So the simplest form of inductive inference is a generalization, and here the evidence consists of a set of examined instances of a phenomena, and the hypothesis is either the generalization itself or a statement about some unexamined instances of it. So Hempel thinks this is a more precise rendering of what constitutes an inductive generalization. You gather evidence from your sample, and then you extend it to your target, right? Now, that target might be an entire class, or that might be a particular instance from the past or from the future. So notice, if a standard example of an inference would be from the evidence statements, all ravens observed so far have been black, we might move to the generalization. All ravens are black. But we also might move to a prediction. The birds now hatching from a given clutch of raven eggs will be black. Or it might be a retrodiction. The raven whose skeleton was found in the archaeological site was black. So notice it's not always moving from the past to the present or the future. It's not always making a just general claim about an entire class of things. It might be particular, it might be about the past, it might be about the future, it might even be about the present. The instance here is you're going from the observed cases to some unobserved case or set of cases. These things, as these examples show, induction does not always proceed from a particular to a general, or from statements about the past or present to statements about the future. More complex and circumstantial kinds of non-demonstrative reasonings might be something like making a medical diagnosis based on observed symptoms, or basing statements about remote historical events on presently available evidence, or establishing a theory on the basis of appropriate experimental evidence. So there are different other kinds of forms of inductive reasoning beyond generalization. However, most of the problems that Hempel wishes to consider can be illustrated by inductions of the simple kind, of a simple generalization. So we won't be talking about these other forms of inductive inference in this presentation. We'll largely be concentrating on generalizations. So first, he wants to examine and ultimately dismiss what he calls the narrow inductivist view of scientific inquiry. Essentially, this is a view of induction and its relevance to science that Hempel thinks is incorrect. He actually thinks it's naive. So he characterizes it, and then he goes on to explain why he thinks this is a bad idea, and we should disabuse ourselves of it. So inductive inference is not an effective method of discovery. That's his main point. There's not some sort of regular process that we can enter into and ultimately discover theoretical answers to particular questions that we might have. There's nothing mechanistic about inductive reasoning. Again, there is no mechanical procedure which leads from observational data to the construction of an appropriate hypothesis or theory. To think otherwise, to think one can mechanically gather data and then generate an explanatory theory, is the naive view that Hempel wishes to criticize. To believe otherwise is to misconceive the role of induction in science, according to Hempel. Hempel terms this misconception the narrow inductivist view of scientific inquiry. This naively mistaken view is articulated in this following quote from A.B. Wolf doesn't matter where, but he characterizes induction this way. And again, this is what Hempel thinks is completely wrong. Quoting Wolf, he says, "If we try to imagine how a mind of superhuman power and reach, but normal so far as the logical processes of its thought are concerned, would use the scientific method, the process would be as follows. First, all facts would be observed and recorded without selection or without an a priori guess as to their relevance or importance. Second, the observed and recorded facts would be analyzed, compared, and classified without hypothesis or postulates other than those necessarily involved in the logic of thought. So we might employ logical reasoning principles. If P, then Q, P, therefore Q. It is not the case that P and not P, right? So logical principles. But other than that, we don't impose any uh, hypothesis or postulates on the facts as we compare, analyze, and classify them. Third, from this analysis of facts, generalization would be inductively drawn from the relations, classificatory or causal, between them. And then finally, fourth, further research would be deductive as well as inductive, employing inferences from previously established generalizations, right? So notice, first we collect facts, then we observe and compare and analyze and classify them. Then we generate our hypothesis, and then we deductively and inductively test that hypothesis. Hempel suggests, however, that previous characterization is highly fanciful, and many have argued against it as naive. But why? Why is it naive? What's Hempel's problem with that characterization of inductive inference and of science in general? Well, for one thing, he thinks inquiry could never go beyond the first stage. Remember, the first stage was supposed to be the data gathering stage. And why is that? Quoting from Hempel, he says, for presumably to safeguard against, to safeguard scientific objectivity, no initial hypothesis about the mutual relevance and interconnections of the facts are to be entertained at this stage. And as a result, there would be no criteria for the selection of facts to be recorded. The initial stage would therefore degenerate into an indiscriminate and interminable gathering of data from an unlimited range of observable facts, and the inquiry would be totally without aim or direction. So this fact-gathering stage that Wolff is suggesting, well, nothing's guiding it. And so what facts does one gather? How does one start collecting them? And when is one done? And when has one got sufficient facts? It seems to be totally indiscriminate, without aim or direction. Again, there's no criteria for the selection of the facts to be recorded, and as a result, the collection becomes indiscriminate and interminable. Note how this critique anticipates the thought of Thomas Kuhn and his contention that science cannot proceed while a research inquiry is still in the pre-science phase, that is, before a paradigm has been developed and adopted to guide the research. Research always requires a reigning paradigm, according to Kuhn, to direct inquiry as to what facts are potentially relevant, and thus which facts to gather and how they are to be compared and assessed. But Hempel goes on to suggest that this highly fanciful characterization of science couldn't get beyond stage 2 either. It could, if it could ever be reached, in other words, if you could ever get to stage 2, and he doesn't think you could, but even if you ever could get to stage 2, which is the comparing and assessing and cataloging and classifying of the facts, the classification or comparison of the data again requires criteria. These are normally suggested by hypotheses about the empirical connections between the various features and the facts under study. But the conception just cited would prohibit the use of such hypotheses, and the second stage of inquiry, as here envisaged, would again lack aim or direction. So for the same reason you couldn't really get to stage 1 because you just have an interminable collection of facts, you really couldn't complete stage 2 either, because you don't know how to compare the facts, what aspects of the facts are relevant, how to classify them, etc. Why is this? Well, again, Kuhn would say it's because you don't have a hypothesis. You don't have a reigning paradigm to guide your research. Again, for the reasons already stated. Could this account, the Wolff account, be retained if suitably rectified? Hempel asks. Perhaps by adding something like, the observation that any particular scientific investigation is aimed at solving a specific problem, and that the initial selection of the data should therefore be limited to the facts that are relevant to the problem. So what if we just said, okay, look, we can't just talk about inquiry, we have to clearly state the problem we're trying to solve. And if we clearly state the problem we're trying to solve, wouldn't that give us more of a direction as to what facts to gather and what are relevant comparisons between the facts? But the question remains then, Hempel would say, what facts are relevant? Again, without an overriding paradigm or hypothesis in the first place, we don't know what facts are relevant. Clearly stating the problem doesn't actually help. The mere statement of a problem alone does not generally determine what kinds of data are relevant to its solution, unless one already possesses a hypothesis as to what facts are relevant. Consider the problem of determining the cause of lung cancer. What sort of data would be relevant? Well, I've clearly stated the problem. I want to understand the cause of this particular disease, lung cancer. Do I gather data about differences in ages, occupations, sex, dietary habits, air pressure, religious denomination, astrological signs? Which of those data are important to the resolution of that problem? Well, notice the statement of the problem itself doesn't give us a hint as to which of these facts we should pay attention to and which of these facts are irrelevant. The notion of relevant facts acquires a clear meaning only when some specific answer to the problem has been suggested, however tentatively, in the form of a hypothesis. Quoting from Hempel, we have, an observed fact will then be favorably or unfavorably relevant to the hypothesis according as its occurrence is, by implication, affirmed or denied by the hypothesis. For instance, we might hypothesize that smoking is a significant causative factor. This then would suggest what data are relevant. In this case, a higher incident of the disease among smokers than among non-smokers would be a relevant fact. Data showing for a suitable group of subjects that this is the case or that this is not the case would therefore constitute favorably relevant confirming data or unfavorably relevant disconfirming data, evidence for the hypothesis. So if we begin with the hypothesis, smoking might be relevant to as a causative feature for cancer, then we would start to collect data among were there higher instances of disease among smokers than among non-smokers? And if the answer to that question is yes, then that would be data favorably related to our hypothesis. It seems to confirm it to some extent. But if the answer to that question is no, then that would be data unfavorably relevant to our hypothesis in that it seems to disconfirm that hypothesis. Conversely, data with respect to cancer rates and hair color would not be relevant at all, given the working hypothesis that is to be tested here. And so these data need not be collected or examined. But were the hypothesis that hair color was a causative factor with respect to cancer, then data should be collected and would be potentially favorably relevant or unfavorably relevant, just as cancer incidences among smokers versus non-smokers would be relevant given the other hypothesis. So generally, what data set is relevant can only be specified relative to a hypothesis to be confirmed or disconfirmed. So one must begin with a hypothesis before one can ever begin one's inductive investigation and perform one's inductive inference. But notice, if you have to start with a hypothesis before you can do the inductive inference, then the inductive inference itself can't be the source of the hypothesis. You have to somehow get the hypothesis some other way, but not through induction. Thus, contrary to the third stage of inquiry offered above, the Wolf account, hypothesis cannot be inferred from the empirical evidence by means of some set of mechanically applicable rules of induction. There is no generally applicable mechanical routine of inductive inference, which leads from a given set of data to a corresponding hypothesis or theory. Induction is not like mathematical operations in the way in which the familiar routine of multiplication leads from any two given integers by a finite number of mechanically performable steps to a corresponding product. So you can have these sort of logical, mechanical operations in math and in logic for that matter, but that's not what's going on in science, and that's not how we arrive at our hypotheses. So he's making a distinction between what others have called the difference between the context of discovery and the context of confirmation. The context of discovery seems to be fundamentally creative and not rule-bound or rule-governed, whereas the context of confirmation might very well be mechanical and rule-governed. Consider, for example, the theory of gravitation. This theory was offered as a novel account for certain previously established empirical facts. So the facts, in this case, the regularity of planetary motions, the facts were already well established. We had the facts for a long time before the theory came along. The theory came along as a novel explanation of the facts we already had. Again, the hypothesis was thought to be a novel interpretation of the facts in the sense that they were, and that means they being the facts, the previously known regularity of planetary motions, had played no role in the description of the empirical facts, which the theory was designed to explain. And surely no set of inductive rules could be devised which would be generally applicable to just any set of empirical data, physical, chemical, or biological, and which in a sequence of mechanically performable steps would generate appropriately novel concepts, functioning as an explanatory theory on the basis of the description of the data alone. So again, the mere description of the facts or the data does not itself yield a novel explanation as to why the data are as they are. Again, they play no role in the description of the empirical facts. I'm repeating myself. Scientific hypotheses and theories, then, are not mechanically inferred from observable facts. Now, maybe this was a long way to go for something that you perhaps had already realized, but Hempel wanted to make it very clear. Rather, they are invented by an exercise of creative imagination. Einstein, among others, often emphasized this point, and more than a century ago, William Whewell presented the same basic view of induction. Whewell says, the process of invention, trial, and acceptance or rejection of a hypothesis refers to the great scientific advances as achieved by happy guesses, by felicitous and inexplicable strokes of inventive talent. And then he adds, no rules can ensure to us similar success in new cases, nor can enable men who do not possess similar endowments to make like advancements in knowledge. So what Whewell is pointing out is that science advances when people have happy guesses. Now, after the happy guess, you go in and see whether that happy guess is true or not, right? So you have to confirm the hypothesis. But the generation of the hypothesis is a felicitous and inexplicable strokes of inventive talent. The chemist Friedrich, and I think it's Kekulé. I thought he was French. All of a sudden, maybe he's not French, but Kekulé, I will say. Most famous work was on the molecular structure of benzene. This might be a story you've already heard. In 1865, Kekulé published a paper suggesting that the structure contained a 6-member ring of carbon atoms with alternating single and double bonds. However, he claimed that the ring formula for benzene molecule occurred to him as he dozed before his fireplace. Gazing into the flames, he seemed to see snakes dancing about, and suddenly one of them moved into the foreground and formed a ring by seizing hold of its own tail. Kekulé does not tell us whether the snake was forming a hexagonal ring, but that was the structure he promptly ascribed to the benzene molecule. So how did it occur to him? He was half sleeping and he was dozing, and it was as if he was seeing snakes dancing around in the fire. Well, that's hardly a rule-governed way. That's clearly a inventive genius, right? So then it would appear that no restrictions or formal procedures are imposed upon the invention of theories. Specifically, scientific objectivity is achieved subsequently by careful testing, observational or experimental investigation. So there does come a rule-governed phase, but the rule-governed phase is not the context of discovery. The rule-governed phase is the context of confirmation. Karl Popper claimed hypotheses are the products of conjectures, which are subsequently subjected to falsification. Hempel here argues, contra Popper, that if careful testing bears out the predicted sequence, the hypothesis is accordingly supported. So this is a subtle difference between the two thinkers, but it's important for us to note. Popper thought you never verify a theory. The most you can do is falsify a theory. If a theory resists falsification, it certainly gains wider acceptance. Once it's falsified, it's rejected, says Popper. But Hempel thinks that no, induction truly plays a role in science, and that inductive positive testing of a theory does lend credence and inductive support to the theory. But here again, we encounter the problem of inductive inference. Normally, a scientific hypothesis asserts more than what it is based on. Thus, it cannot be inferred from a mere finite set of consequences that to which it may have been put to the test, right? But why? Because it's claiming general principles, not that a finite sort of set of things has happened, but that an infinite set of unobserved things has or will happen. Therefore, even strong evidential support affords no conclusive proof. It is precisely this fact, of course, that makes inductive inference non-demonstrative and gives rise to Hume's classical problem of induction. Again, therefore, even strong evidential support affords no conclusive proof. But of course, what does one mean by conclusive? It was already agreed rather, that inductive inference is non-demonstrative, which gives rise to Hume's problem. Perhaps we need a different standard of credence then, right? So granted, we're not getting from induction what we get from deduction, but what are we getting from induction? And what is this other kind of credence afforded by inductive inferences? So this is what Hempel invites us to consider. What Hempel is pointing out is that we need not only a standard of sufficient evidence for inductive proof, but perhaps more fundamentally, a clearly articulated notion of what constitutes inductive inference itself. This latter project, he believes, precedes the classical problem of induction. In other words, first we need to get clear on precisely what inductive inference is, before we can ask the question as to whether or not it provides warrant for belief and under what conditions. Karl Popper, though, was a strident critic of induction and actually claimed it plays no role in science whatsoever. Popper claims inferences involved in scientific testing are deductive from the theory to implications about empirical facts and never in the opposite direction. Induction, Popper claimed, is a myth in science. It doesn't really occur in science. Again, this is Popper's opinion. It is neither a psychological fact, nor a fact of ordinary life, nor one of scientific procedure. And it is essentially this observation which Popper holds solves Hume's problem of induction. So Popper thinks the problem of induction that offered by Hume is solved by the fact that scientists don't use induction. Now, frankly, Hempel and many others think that Popper's being unreasonable here and that induction is used in science. But to get to Popper's point here, right, he claims that the way science is actually conducted is we reason like this. Oh, rephrase. Here's what the inductivist seems to be saying. The inductivist seems to be saying that if my theory H is true, then result R will occur when I conduct this experiment. I conduct this experiment and R occurs. Therefore, my theory H is true. But what Popper points out is that is fallacious, right? This is the fallacy of affirming the consequent. If P, then Q, Q, therefore P. No, it doesn't work that way. Again, the fallacy of affirming the consequent. Notice, strictly speaking, logically speaking, deductively speaking, nothing follows from the conjunction of those two propositions. If P, then Q, Q. So, right, nothing follows from that. So, according to Popper, we cannot verify or confirm a theory inductively. All we can do is deductive, right? According to Popper, science must not try to verify theories, but rather science must seek to falsify theories. We start off with, if theory H is true, then experimental result R will occur. But R does not occur. Therefore, hypothesis H is not true. Now that is a logical, deductively a logical argument, valid argument, right? If P, then Q, not Q, therefore not P. So for Popper, science doesn't proceed by verifying theories. Science proceeds by attempting to falsify theories. When falsified, science can move on and come up with some new theory because it rejects the theory that's been falsified. If a theory resists falsification, it hangs around. But he basically thinks all scientific theories are merely in the state of not having been falsified yet. This is the deductively valid inference called modus tollens. If P, then Q, not Q, therefore not P. Theories which resist falsification, Popper maintains, rightly gain our tentative acceptance. But this is also why Popper claims that science advances by deduction, not induction. But Hempel disagrees. While empirical science is not inductive in the narrow sense, the naive sense that he's criticized earlier, it still may be said to be inductive in the wider sense. While scientific hypotheses and theories are not inferred from empirical data, they are accepted on the basis of observational or experimental findings, findings which afford no deductively conclusive evidence for their truth, but nevertheless findings which suggest their truth. So in this sense, science does proceed by inductive, non-demonstrative inference. Thus, the classical problem of induction retains its import. In other words, Hempel thinks we do use induction, and we can't just dismiss Hume by saying, well, we don't use induction. What justification there is for accepting hypothesis on the basis of incomplete evidence, well, that problem remains. There arises then the logically prior problem to the classical problem of induction, that is, of giving a more explicit characterization and precise criteria for what counts as acceptable inductive reasoning in science. Briefly, an analogous problem for deductive reasoning. I think I want to pass on. It's in the notes, so I'm going to pass on. So, how does induction proceed then? What is the nature of an inductive inference, right? Well, it might say that we gather evidence E, and E supports the hypothesis H, therefore we accept hypothesis H as true. Schema 2 is slightly different. We gather evidence E. E does support hypothesis H, but only to some degree, relative to some degree. So it's not an all or nothing deal. It's probabilistic, and it comes in degrees. Therefore, we accept H as probably true, where probably is understood as a degree of probability, right? So again, this would be a notion of induction that is sort of qualitative versus quantitative. The first schema treats inductive support or confirmation as qualitative concept. Such rules would need to specify conditions under which a given set of evidence supports or confirms a given hypothesis completely. Here, it is an all or nothing game, in the same way that argument is either deductively valid or not. So the first schema, which sees inductive inference as a qualitative concept, says, look, evidence set E either possesses the necessary qualitative feature or it does not, right? Just like you're either pregnant or you're not. It's either valid or it's invalid, or it's qualitatively confirming evidence or it's not, right? That's one schema. Hempel doesn't think that's going to be very successful. So he wants us to consider schema number 2, where inductive support comes in degrees, quantitative concept. Thus, rules would need to provide criteria for determining the degree of support evidence lends to the hypothesis. These criteria might even amount to a general definition assigning some definite value of R, 50%, 80%, 90% sure, etc., to any given hypothesis H with evidence set E. So given E, we believe that H is 90% confirmed, or 80% confirmed, or 50% confirmed, or something like that. This is one of the this is one objective of Rudolf Carnap's inductive logic. Don't worry about that. But Rudolf Carnap worked on trying to come up with such quantitative rules for assessing the degree of support a set of evidence provides to a given hypothesis. The formulation of rules of these or similar kinds will be required to explicate the concept of inductive inference in terms of which the classical problem of justification is formulated. And it is in this context of explication that the newer problems of induction arise. We now turn to one of those problems. It concerns the qualitative concept of confirmation. So we're going to look at paradox of qualitative confirmation, specifically Nico's criterion. Now, Nico was French. I might have gotten him mixed up with Cafcoulé, but Nico was a French logician and mathematician and philosopher. What rules might we use to when making inductive generalizations? So what's going on? What's the procedure? What rules might we invoke? Well, consider this. If all cases of F that have been found so far are also cases of G, then we might inductively conclude, therefore, that all Fs are Gs, right? So that would be one way of doing an inductive generalization, and it's based on the fact that all cases of F that we've encountered thus far have been cases of G, and we generalize to say that all Fs are Gs. So we have a hypothesis, for instance, that all ravens are black. If you want the logic for that, there's quantitative logic. Maybe some of you have had logic in the past, and you recognize you're saying, for all X, if X is a raven, then X is black, right? So the logical formulation is here, symbolic, and that's the English translation of this formula. For all X, if X is a raven, then X is black. H, our hypothesis, all ravens are black, is supported or confirmed by a positive instance of I, a positive instance rather, I. In other words, a black raven. So each time we encounter a black raven, we've encountered a positive instance of our generalization. Our generalization is all ravens are black, and so any black raven is a positive instance of what it is we're alleging, right? That is, it's a raven and it's black. On this view, any evidence sentence of the form, this is a raven and this is black, lends inductive support to our hypothesis. Let us refer to such instances as positive instances for type type I for H. So I for H, a positive instance for H would be anything of the form, this is a raven and this is black. Conversely, our hypothesis H is disconfirmed by any evidence sentence of the form, this is a raven and this is not black, right? Our I and not BI, right? So our generalization was basically saying there aren't any of those things around. There's nothing around that's a raven and fails to be black. But if we come across such a thing, it is a raven, but it's not black, well, our hypothesis has been disconfirmed. This formulation was advocated by the French logician and philosopher Jean Nicot, I think it's Nicot, to test the relevance of evidence for an inductive confirmation of a generalization put forward by the French philosopher Jean Nicot, saying that for a generalization of the form all A's are B's, any instance of this A is a B provides confirming evidence. Any instance of this A is not a B disconfirms the generalization and justifies its rejection. And any evidence of something which is neither an A nor a B is irrelevant. That is, it neither confirms nor disconfirms. Okay, so far so good, right? This seems to make sense. I have a generalization, all A's are B's. If I run across an A that's a B, that seems to confirm my belief that all A's are B's. If I run across an A that is not a B, that seems to disconfirm my belief. I have evidence now that my generalization is false and I should reject it. And if it's not an A or a B, well, then it's just irrelevant to my generalization. And that seems to be a key point that Nicole is making here. So, okay, so far so good. This certainly seems reasonable enough. Any positive instance I confirms theory H, any negative instance of I disconfirms the theory H, and any instance that is neither I nor not I, neither confirms nor disconfirms H. But Hempel points out that H, our hypothesis, is logically equivalent to the statement H prime. In other words, our generalization under consideration, all ravens are black, is logically equivalent to the statement, all non-black things are non-ravens. If you've had introduction to logic, maybe you realize, right, when you reverse the terms, that these are logically equivalent. When I say all ravens are black, I'm saying the same thing as all non-black things are non-ravens. Thus, for all X, if X is a raven, then X is black, is logically equivalent to the statement for all X, if X is not black, then X is not a raven. But this means that all ravens are black is logically equivalent to all non-black things are non-ravens. So far, so good, right? Oh, and that's just giving you the logic there. Okay, fine. Okay, so what's the problem, right? It doesn't seem to be a problem, right? So far. Well, here's the problem. What would be a confirming instance of our hypothesis H prime? Remember, H prime is all non-black things are non-ravens. Well, some I, right? It'd be some instance of a thing that is a non-black and is not a raven. So what's a positive instance for H prime? I is not black and I is not a raven. According to Nico's criterion, then, this generalization, H prime, all non-black things are non-ravens, is confirmed by any positive instance. That is, by any individual instance of something being not black and not a raven. In other words, we said that already. But since H prime expresses exactly the same assertion as H, any such instance also confirms H. But now remember, what's the positive instance? Anything that is not black and not a raven. Such things as yellow roses or a green caterpillar or red herring confirms our generalization, all non-black things are non-ravens. Why? Well, because a yellow rose is a non-black, non-raven. A green caterpillar is a non-black, non-raven. A red herring, you see the problem. But notice, if that confirms all non-black things are non-ravens, and if all non-black things are non-ravens is logically equivalent to all ravens are black, then that means a green caterpillar confirms our hypothesis all ravens are black. Again, since H prime expresses exactly the same assertion as H, any such instance will also confirm H. Consequently, such things as a yellow rose, a green caterpillar, or red herring confirms the generalization that all ravens are black by virtue of being a non-black, non-raven. So that's the problem. If I said to you that a black raven confirms our hypothesis, all ravens are black, that seems reasonable. If I told you that a green caterpillar confirms our hypothesis that all ravens are black, you'd find that odd. Except it seems to fill the bill. But wait, it gets better. Next, our hypothesis H is logically equivalent to the following H prime prime. For all X, if X is a raven, or if X is not a raven, then if X is not a raven, or X is black. Let's try that again because I messed it up a little bit. For all X, if X is a raven or X is not a raven, then it's the case that either X is a raven or X is black. In other words, for anything that is a raven or that is not a raven, in other words, for anything at all, right? A raven or not a raven. Well, that's everything, right? Because everything is either a raven or it's not a raven. So if anything is a raven or not a raven, i.e., if anything at all, either it's not a raven or it is black. Confirmatory instances of H prime prime would be any instance of a non-raven thing, such as a tennis shoe, or any instance of a black thing, such as a black frying pan. Right? Why? Well, for anything in the world, either it's black or it's a raven. Oh, wait, or it's not a raven, rather. Either it's black or it's not a raven. Well, that's confirmed by black ravens, yes. That's confirmed by non-black tennis shoes, yes. That's also confirmed by black frying pans. But recall that H prime prime, as with H prime, is logically equivalent to our original hypothesis. All ravens are black. Thus, a confirming instance of all ravens are black would be any instance of a thing that is not a raven, or any instance that is a black thing, whether it's a raven or not. Again, anything that's either not a raven or is black. Those are confirming instances of our hypothesis for all X, either X is a raven or X is black. So that would be confirmed by a black raven. R is a raven, I is a raven, and I is black. That seems to make sense. But this is also a confirming instance as well. This condition is met by any object I that is not a raven, whether it's black or not, and any object I that is black, no matter whether it's a raven or not. On this view of inductive confirmation, any such object affords a confirmatory instance in support of the hypothesis that all ravens are black. So again, if I thought, what confirms a hypothesis all ravens are black, and you told me a black raven, that makes sense. If you told me a green caterpillar, I would find that odd. And if you told me a tennis shoe, it doesn't matter what color it is, I'd say, how does a tennis shoe confirm the hypothesis that all ravens are black? Well, by confirming the logically equivalent hypothesis that for anything in the world, either it's not a raven or it's black. But wait, it gets worse. H is equivalent to H prime prime prime. And H prime 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 is logically equivalent to the claim for all X. If X is a raven and X is not black, then it is the case that X is a raven and X is not a raven. Trust me, the logic works on this. In other words, if anything that is a raven and is not black, then that thing is both a raven and it's not a raven. This is confirmed by any instance of something which is a raven and is not black, such that it also meets the conclusion it's a raven and not a raven. However, this formulation, this is H prime prime prime, third, right? Nothing can possibly count as a confirmatory instance of this generalization, since the consequence can never be instantiated. Let's go back for a moment, right? So the consequent of this conditional is something is both a raven and is not a raven. Well, we know that could never happen. Well, if this could never be true, this consequent, right? Then this conditional can never have a positive instance. That is, this conditional can never be instantiated, since nothing can both be a raven and not be a raven at the same time. So there is no confirming instance of HIII, and therefore it would seem no confirming instances of HII's logical equivalent H. So that's, again, the mystery deepens, shall we say, right? How is it that there can be no positive confirming instances for this conditional or this generalization, when this generalization is logically equivalent to another generalization for which there can be confirming instances? Again, that's why it's called the problem of inductive inference or inductive confirmation. These peculiarities and some related ones, and the notion of confirmatory instance of a generalization, have come to be referred to as the paradoxes of confirmation. At first glance, they appear to be implausible and perhaps even logically unsound. But Hempel claims that on further reflection, we may regard them as perfectly sound, and that our intuition in the matter is what leads us astray. Right? So he wants to say, well, they're not really as odd as they think, as you might think. Now, I think I'm going to wrap things up here because we're closing in on an hour, and I don't like taking too much more time than an hour. And the main thing I wanted to get through on this set of notes was the paradoxes of confirmation and why it is that the generalization, all ravens are black, could be construed as being confirmed by a yellow butterfly or a tennis shoe of any color. So you have the notes. Naturally, if you have questions on this, you want to discuss it with me further, do more research, etc., please let me know. I'd be happy to respond to those inquiries. And I wish you a good rest of your day.